Hello everyone. In this session, we will discuss about the closed loop speed control of DC drive. So this is a crucial topic because modern electric drives, which demands the accuracy, stability, and disturbance rejection. So today we will understand why this closed loop is important and why the open loop control system which fails, and what are the feedback which improves the performance of the overall systems. And we have various sensors used for the speed measurements and various PWM power stages we have implemented. So next is a quick recap before entering into the closed loop system. That is what we have covered so far. First one is the open loop system. Here there is no feedback, so we have a simple system but which has inaccurate one. And second is the system dynamics. Here we are dealing with the transfer function, poles, zeros, and stabilities. And third one is the speed control basics, which has the motor characteristics and speed torque characteristics of this motor. Next we will go for the mind map. So here which this slide which connects the motor, controller, feedback, and your power electronic devices. So the closed loop control which integrates all these blocks into it for a self-correcting system. Next one is the open loop fails. What is the actual problem we are facing it? The open loop system which fails because of it real world disturbances. That is the load variation which drops the speed, and the temperature changes which also affects the parameter variations, and we have supply fluctuations which also affects the voltages, and there are aging components which produces the drift. Since there is no feedback, the system cannot correct the errors automatically. Hence, the feedback is essential. Next is the speed sensors and the entire feedback. To implement the closed loop control, we must ensure the actual speed. What are the common sensors we are using here, which is first one is the optical encoders, which has high resolution and which produces the digital pulses and which is suitable for the precision dies. Next one is a tacho generator, which has the analog voltage which is proportional to the speed and which is more simple and reliable. And third one is a Hall effect, which has a contactless and which is more suitable for the even in the harsh environment. So all these sensors which converts the mechanical speed into the electrical systems. Next is a closed loop architecture. So we have the reference speed, which is a set point, and error detector is here, and the controller, and we have the motor drivers. Along with this, we have the feedback sensors, and which is working based on the errors. That is, the error can be calculated from the reference speed along with the actual speed. That is the difference between the reference speed and the actual speed. So the controller which processes these errors and generates the control signals. If the load increases, the voltage and the speed gets dropped, which can create the error as an increased one, and the controller increases the voltage, there comes the speed is restored. So this is the automatic correction over here. And the closed loop speed controller, here we can see about the complete block diagram. We have the references, comparators, controllers, which is connected to the PWM drives, and we have motors, sensors again, which has a feedback system. So this form a closed loop. So this closed loop system which provides the accuracy, stability, and also there is a rejection in our disturbances. Next is the tuning for performance. We have the PWM, sorry, PID controllers. So most of the DC drives uses a PID controller. So now we have to understand the each parameters. We have the rise time. So this is how fast the motor reaches the set speed, and there comes we are increasing the KP value for the faster responses. And next is the overshoot here. So we have a speed which is exceeding the reference value, so we can reduce the KP value, and also we can add the KD values. Next is the steady state error, which remains the error after the settling, which increases the Ki value. And last one is the stability, which avoids the oscillations. And we have a proper tuning is required. And the we have common tuning methods as Ziegler and Nichols, and we have trial and error methods. And also we are using for the software based tuning is also there. And we have the power stages, which is the which has the driving part. So here the controller output is not directly applied to the motor, so it goes to the PWM based motor drives. So we are dealing with again the duty cycles, and the switching frequencies are also very high, which has 10 to 20 kilohertz over here. And we have certain key components is also there, that is MOSFET or IGBT, which is a fast switching. And we have great drivers there, the signals are isolated, and we are going for the amplification purpose also. And we have the snubber circuit, which will act as a protection against the voltage spikes. Then we have H bridges, which will do the bidirectional controls. And this PWM ensures the high efficiency as well as the smooth voltage control. Next, we have certain key points and the summary of this presentation. So let us summarize the feedback, which eliminates the uncertainty, and the sensors, which measures the actual speeds. And we have a PID controller, which optimize the dynamic responses. And finally we have the PWM, which provides the efficient power control. So the closed loop system, which are very superior than the open loop system in all the performance metrics. And we have certain references and for future reading. So for deeper understanding, we can go through these books and journals for our understanding. So I hope you have understand about this concept. So we can meet in the next video with some other interesting topic. Thank you.